Hello, everybody. Welcome to the radio. This time, we're going to talk about the neural special Jacobian matrix for backpropagation algorithm. And in the last video, we talked about the multivariable chain rule, and then we come out a relationship of the partial derivatives between the different layers of a fully forward symmetrical network, which looks like a neural network. In this video, we will apply that relationship in a neural network example we used in the neural network notation video and other videos. So it will be the same uh, network model, which is a three-layer simple neural network model. So as we can see here, we have three input and a three layer, and the last one is a cost function used to evaluate the performance of the neural network model. And we already talked about the forward calculation in the notation video, and here we just talking about the backward. So in order to update the parameter, which is a weight and the bias for each layer, we have to come out the gradient matrix to update all the parameters. And so we, for different layer, we have to update from the cost function all the way back to the fourth layer. We observe the structure. Our concern is all the weight between the layers in this drawing, and but in order to get to the gradient matrix of the weight and the bias, we have to come from the cost function step by step to calculate the gradient. For example, if we start from the cost function, we have to get the partial derivative of the cost function to the active function output of the layer 3. Then this gradient has to transfer to the net input of layer 3. Then we get the gradient for the weight for the layer 3. And after this calculation, we have to go to the second layer's weight matrix. And then we have to propagate the gradient from the net input of the layer 3 to the neural output of layer 2, then from the neural output of layer 2A to N, then we'll calculate the gradient for the W, which is weight again. So this will be the sequence we're going to use in this calculation for the backpropagation. And I draw a few right line here, and the key calculation is for the gradient partial derivatives. The first one's from cost function partial derivative to the net input of third layer, and then will be the second layer, and then will be the first layer. Once you have the cost function partial derivative cost function to the net input for each layer, then you can calculate the partial derivative for all the weight for that layer. And this is how the backpropagation is updating all the weight parameters. So in this video, we will only focus on the special Jacobian matrix. So in the last multivariable chain rule video, we can see that the part derivative for different layer is the relationship is a Jacobian matrix. And the good thing about the neural network, because its structure and the Jacobian matrix between the different layer has some special features which make it more convenient for the calculation. So we will start from the right to left, talking about all those special Jacobian matrix. First one is we can see it's initial. We call it it's from cost to the A, which is neural output of the third layer, which is very close to the cost function. So partial derivative of the cost function to the neuron output A or layer 3 is very easy. It's known because After the forward calculation, you got the model output, and then you also has the correct uh, y value. So and you have your children cost function, and this partial derivative has the formula and you know all the numbers. So this one's kind of like initial. You will know it once you design it and fill in all the numbers. Then the next after we have the we build the relationship between the C and the A, then we need to build the Jacobian matrix for A and N of their three. And as we're showing in this here, we just do first step. We write the fully collected Jacobian matrix. It's basically partial A, layer 3, 1, uh, or partial n necessary 1, we write the 1 1 1 2 2 1 2 2. It's a fully full form of Jacobian matrix. And we can see the feature here is the A1 basically only depend on the A1. So we got, and you do the partial derivative pretty much it's a partial is derivative of the activation function. And we know that A1 has nothing to do with the second neuron or nursery's net input. So basically zero. Similarly, we know that A32 has nothing to do with N31, so basically it will be zero, and it only related to the net input of second neuron. So it's a derivative of the active function here. So this Jacobian matrix you will see is a very easy form. It's a diagonal matrix, and which make it very easy to calculation. Basically, you know the active function, and in the forward calculation, you know the n, and you pretty much got this matrix. So this step is done, and after we got the n, and the next step we should go to calculate the partial derivative of the with W, but the W is kind of weight kind of a little bit special. So here we will talk the another simple uh, Jacobian matrix. We basically jump from N to A, basically build the collection between the third layer's net input and the second layer's neuron output. And for this one, I will just call it JNA. And for example, I use an example of layer 3's, basically J3 sub NA. Here, similarly, we write the full form of Jacobian matrix that we just observe the lightwork structure. And we actually can easily say that this Jacobian matrix, it happens to be the weight matrix. So when we do the forward calculation, we already initialize the weight. So this one is also annoying. So basically, with with all the special geometry on this side, one thing they can do it, you can see, I can if I have say a Jacob the partial derivative c of a partial c partial a, then using JAN I can jump to the I can get a partial derivative of partial c partial n, and then I have the Jacobian between n and a, then I will have the partial derivative of the partial derivative c respect to the partial derivative a for the next layer, and then using a n again. So basically, you can see I can get all the partial derivative of a and n in this network. So this is the special geometrics just for the neurons net input and the neuron output and the cost function. And we already see they have very good form. One is a diagonal matrix, the other pretty much is a weight matrix, and they are knowing if you go do the forward calculation. And then the next step, we're going to talking about the how you get the Jacobian matrix from n net input to the weight and the bias. So this one it has a little bit tricky, and there's some you have to think about twist their thinking a little bit. So basically, we can see one thing I have to mention is the weight is not on our so-called dependency diagram if you think about the multiple chain rule, but it's on the branches. But here, what you need to think is when you got the partial derivative of cost function to the net input, when you come at here, you at this point you forget about the neuron output from last layer. Now you think your dependent variable is W. And in that case, you can still use a Jacobian matrix to get the partial derivative relationship between N and W. As I mentioned, we just call it Jacobian NW. For example, we use a layer 3 as an example. So there's we basically know there's two light input of the layer 3, and we know there's 4 weight for this layer. So we basically write the full Jacobian matrix. Basically, it's N1 partial derivative with respect to all the weight of this layer, and the same thing we do the let input our second neuron with respect to all the weight for this layer. And then after we have this Jacobian matrix, then we observe the structure. We can see that the first neurons let input only related to the two weight, which is W311 and W312. So, and we can also we know from the forward equation, we know that partial derivative is the neuron output of the second layer. So we basically write the A21, A22 here. And we know this last input has nothing to do with the weight related to the second neuron, say. So this element and this element is 0. And a similar situation happened on the second row. So we got the original Jacobian matrix between the net input and the weight. And this is the reason we call original one, because one thing we noticed in our multiple variable chain rule Jacobian matrix derivation, and what I wrote is a row vector for the cost to the weight of this layer. But one thing we noticed is when we do the weight update, we actually need a matrix of weight matrix here to so we have an easier life to all the average calculation based on weight matrix instead of a weight function. So now we got to do a second step. So we have to think how are we going to convert this weight vector to a weight matrix. And you don't have to do this because this also works. But what I'm trying to say is if you want to get a consistent form used in the back propagation, you probably have to convert this weight vector to a weight matrix. And in order to do this, I don't think there's any rock science to do this. So the reason I write this part is I just using brute force. You can this a vector, right? I just write it to a matrix, and I know it is equal to the row vector or partial derivative cost with respect to the net input, and then it's the full Jacobian. So I just sit there, I write this in a matrix. I'm thinking how I'm going to convert this to a weight matrix and still hold this relationship. So there's no theory here. So because the good thing is I already know we have to do this matrix. So I just find a piece of paper and I just try it, because this is 1/4 matrix. You can think the vector as a 1/4 matrix. Then this suddenly become a 2/2. And the original is like a 1/2 matrix multiplied by 2/4. So I just spent like a 2 hours just try how am I going to make it a matrix. So and now I just convert it to a 2/1. I pretty much is just transpose this partial derivative matrix, and then I just take the first two element of this 2/4 matrix, put it here. So you got a 2/1, 1/2, you got a 2/2. And then by doing this, we converted this original Jacobian matrix to a special 1 by 2 matrix. And one thing we have noticed when I derive all the Jacobian matrices during the multivariate chain rule, in order to get a good looking Jacobian, I did make everything a row vector. And here, so we have to do a transpose of the partial derivatives. This will be the transpose. The transpose happened here. And after we're doing this, the JNW, I call it JNW, for layer 3 is transpose. It become a row vector, which happened to be the output of the layer 2, which looks very neat also. And we can do the similar thing to the bias, because the bias and the weight pretty much the same thing. I didn't draw the bias here. Each neuron got a bias. And the only thing is here, instead of is the output of the second neuron's output, and for bias, it become 1, because we know you pretty much the forward calculation is W x or WA plus a B. So that means the B's parameter actually is 1. So after you do a partial derivative with respect to B, you pretty much got a 1. So similarly, for this Jacobian matrix between N and B, after transpose, you got a 1 and a 1, and pretty much just you don't need to calculate, you don't need to multiply anymore, because it's just a 1. so so that's all of it. And you can see we got the we got the partial cost respect to the last layer's output. It's kind of annoying, as I mentioned at the beginning. And then we have the Jacobian matrix between the neuron output and the net input. And we also got the Jacobian matrix between the last layer's output and the next layer's net input. And so pretty much with these three, we can jump between any point of any layer of this neural network. And then once we got the Jacobian matrix between N and W, so basically which means once you jump on any of the net input, you can easily jump to the weight layer to get the weight layer's partial derivative, which pretty much is his gradient matrix. We can use that gradient method's formula to update the weight parameter and the Bayes parameters. So that's pretty much all about this video. And just a quick summary of this. So basically, we presented all the backward special Jacobian matrix. Once we got this special matrix, we can jump at any point, any layer for this network model. And this actually is very good to can provide all the Lego pieces to build the backpropagation algorithm. And so that's pretty much all about the video this time. At the beginning, I planned to do the backpropagation in one video, but when I prepared the notes, I found out it's kind of will be very busy. I will separate the two. So this one we're only talking about the Lego pieces, which is all the special Jacobian matrix for the backpropagation. In the next video, we will have I plan to do the notes, and then we have showing all the forward calculation and the backward calculation. Since if you watch all the video before this one, you will have all the formulas and the metrics from input to output to the cost function. And this video provide you with all the gradient and the Jacobian matrix. Then you can go backward to any layer you want. And that's pretty much of this video. Thanks a lot for your time, and we will see you in the next video, which will talk about the backpropagation algorithm. Thank you. Bye.